Good morning, everyone. Today, I'll present our research titled Benchmarking Segmentation Models for Food Image Recognition, which has been presented in ICC-SCI 2025 by our team from BINUS University, which consists of Jessica Wibowo, Eric Tianto, Aretha Natalova Wahyudi, and our lecturer, Edbert Sebastian. Food image segmentation is critical for dietary monitoring, as poor diet is now a leading cause for global mortality. However, it is challenging because food lacks consistent shapes, has overlapping textures, and varies across cuisines and lighting conditions. These factors cause traditional methods to fail, making accurate segmentation essential for nutrition applications. Key challenges include: first, amorphous shapes without fixed geometry. Second, overlapping ingredients and occlusion. Third, high visual variability in plating and style. And lastly, lighting and angle distortions. All of these make boundary detection very difficult. Our objectives were: first, to benchmark three CNN architectures, naming FCN, DeepLab-P3, and PSP-NAT on FoodSeg 103. And the second is testing the hypothesis that simpler architectures generalize better for food segmentation. In this project, we used the FoodSeg 103 dataset from Hugging Face. This dataset consists of 7,000 food images with pixel-level masks for 103 ingredient categories. This makes this dataset ideal for real-world segmentation scenarios.
So in this study, we evaluated three widely used semantic segmentation models, namely PSP-NAT, DeepLab-P3, and fully convolutional network, or FCN. These models were selected because they represent different strategies for capturing contextual information and spatial details in images. The first model is PSP-NAT. PSP-NAT employs a pyramid pooling module, which allows the network to aggregate contextual information at multiple scales. This multi-scale representation helps the model understand both global scan, context, and local object details, making it particularly effective when object appears at varying size within images. The second model is DeepLab-P3. DeepLab-P3 leverages a source spatial pyramid pooling, or SPP, to expand the receptive field without reducing feature selection. This approach enables the models to capture richer semantic segmentation and produce more accurate segmentation, especially around object boundaries and point structures. The third model is FCN. FCN is the simplest architecture among the three and serves as a strong baseline. It uses skip conventions to combine low-level spatial features with high-level semantic features, allowing the model to preserve fine details while maintaining semantic consistency. In summary, PSP-NAT is effective at handling scale variation due to its pyramid pooling strategy. DeepLab-P3 performs well in capturing object boundaries and complex structures through SPP. Meanwhile, FCN is a lightweight and computationally efficient, making it suitable as a baseline model. To ensure a fair comparison, all models were trained under identical conditions, including the same dataset, number of training epochs, and optimization settings. As a result, the performance difference observed reflect the inherent characteristic of each model rather than difference in the training setup.
So for the results, we can see that quantitatively, using MIOU metric, or mean intersection over union, we can see that FCN achieved the highest score, followed by DeepLab-P3 and then PSP-NAT. Another significant finding is that the FCN here even beat FoodSem's reported MIOU in this dataset. And we can see this also happening visually, which the FCN outperformed the others, especially for small or overlapping food items. And DeepLab-P3 also performed well, specifically for edge-sensitive areas. It maintains a smooth contour around the food. PSPNet, however, lagged behind. It struggled with complex boundaries. And then this brings us to our conclusion, which directly supports our initial hypothesis. Simplicity often works best. And our results demonstrate that simpler architectures like FCN are more robust for this specific task. This is likely because it has fewer parameters and a lower tendency to overfit compared to heavier architectures. However, limitations remain. Our dataset that we use here, the FoodSec103 lacks global cuisine diversity and also uncontrolled smartphone camera conditions. Also, newer architectures like transformers diffusion models as well as cross-dataset transfer were outside of our scope. So overall, this work demonstrates that well-tuned classical CNNs can still outperform newer foundation models in niche domains. And also here were two of the main references that we used. And thank you so much for listening.